divergence criterion for functional limits, which is really kind of a nice way to use sequences with these functions. That is, suppose you have a function with domain A and C is the limit point of A. If you have two sequences, xn and yn, such that C doesn't appear in either one, but the sequences both converge to C, but f of the sequences do not converge to the same thing, then the limit of the function does not exist. Now, the advantage of this is that dealing with a function, x goes to C, that involves the delta. It basically involves an uncountable number of possible values for x, and that's hard. I don't want to deal with an uncountable number of things. So this allows us to work with just a countable number of things by looking at the sequences. So there's an example in the book, but I'm going to give you a more concrete example. And that is, here is a function, and I'm going to draw, there's axes, here's a function in red. Right, so it just goes on, continues on and on, so this is a value of 1. So basically what I have is f of x equals 1 if x is less than 0, 0 if x is bigger than or equal to 1. And what I'm going to show, that the limit as x approaches 0 of f of x does not exist, and I'm going to do it by using exactly this. I'm going to come up with two sequences. They're going to both converge to C, in our case it's 0, where the limits are both going to be C, but the values of the functions, the sequences involving the values of the functions are going to be different. So I need to pick two functions. Let x sub n equal 1 over n, and y sub n equal negative 1 over n. So pretty clearly, both of these are going to go to 0, which fulfills this part of it. And I'm going to show that these limits don't end up working out the same. So I need to figure out what f of x sub n is, and I need to figure out what f of y sub n is. F of x sub n is f of 1 over n. 1 over n is positive, so that means that the value has to be 0. F of y of n is f of negative 1 over n. That's going to be negative, so f of negative 1 over n is going to be 1. So what I get is that the sequence f of x sub n, that's just equal to, right, the sequence of 1 over n, which equals a bunch of zeros, which equals 0, 0, 0, da, da, da. That's clearly going to converge to 0. Whereas my sequence of y over n's, or y of n's, is equal to a sequence of negative 1 over n's, which equals 1, 1, 1, 1, 1, which equals the sequence of 1's, which is going to converge to 1. The key thing here is that the limit of this and the limit of this are not the same as up here. So these are not equal. So these things, 1 over n converges to 0, negative 1 over n converges to 0, but f of 1 over n converges to 0, and f of negative 1 over n converges to 1. So this allows us to conclude that limit as x goes to 0 of f of x does not exist. Because if it did exist, basically the values would have to be the same wherever you go, whether you approach from the right or the left or however. But in this case, the values as you approach from the right are different from the values you approach from the left, so they're not the same. By the way, it doesn't always have to be that one approaches exactly from the right and one approaches exactly from the left. It's very convenient for this example, and it's frequently convenient for these problems, but you don't have to have it. That's not an ironclad law. That's how it works.